a PhD dissertation defense exam. Thank you for coming. It's my pleasure to introduce him to you. Mahmoud came to me, well, some time ago. It was 2017, I guess. He's done a lot of work since. His work ethic is unparalleled, and he does excellent quality work. He's one of those type of people who is not afraid to dive into new materials, things that what others might find outside their comfort zone. He says, yeah, sure, let's try that. So he's already published and presented his work over a dozen times at conferences. He has 2 published journal papers and 4 more pending. They're either being reviewed right now or they're about to be submitted. He's also worked on, he has won awards for both his GA skills and as well as his entrepreneurship skills. And he's also served in some internships with companies, both local and on the mainland. So without taking up any more of his time, I'll hand it over to him and let him tell you about his work.
Thank you, Dr. Lubicki, for your kind introduction. So the title of my presentation is Non-Contact and Secure Radar-Based Continuous Identity Authentication in Multiple Subject Environments, and I welcome you all to my presentation. So these are the overview of my presentation. I will talk about basics of introduction of the Doppler radar-based non-contact monitoring. Then I'll describe about the research challenges to implement this sensor technology for multi-subject scenarios. I will also describe about the security aspect of this particular sensor technology. And then I will talk about experimental setup and hardware. I will try to describe in details about my proposed application, and finally it comes results and conclusion. So non-contact vital sign monitoring using microwave Doppler radar has shown great promises in healthcare application and has become an active area of research and study for about 4 decades with proof of concepts demonstrated for various applications. It has several potential advantages. First of all, it's a non-invasive technique. Then it's a wireless technique. So that means no wiring need to be attached to the body. So definitely it's a comfortable technique. There are several potential applications of this technique. First of all, it can be used for sleep apnea because sleep apnea patients need to wear a bulky device to monitor their respiratory pattern during sleep. It can also be used for sudden infant death syndrome because infants cannot put the respiratory monitoring devices on their chest surface. Similarly, it can also be used for burn victim patients. So for this particular project work, we are focusing on security and government applications. More specifically, we are testing the feasibility of our proposed system for one particular medical testing application, that's in-home sleep apnea testing, and I will describe in details about it in my next slides. Before that, now let's have a look what are the existing traditional authentication system. So fingerprint is the most reliable and trustworthy traditional identity authentication system. Then comes password. Facial recognition using intrusive video camera imaging is also very popular. People also attempted to recognize people from their walking pattern, like gait-based recognition. Then physiological biometric-based approaches are also gaining popularity. However, it requires contact sensor. Home-based sleep study is also gaining attention, and it is a recommendation from American Academy of Sleep Study Machine that there needs to have some kind of identity authentication system that need to be integrated with the home-based sleep study machine to make sure that data falsification doesn't occur. So now let's have a look what are the drawbacks of the traditional continuous identity authentication system. So the first drawback is a vulnerable one-pass validation system. That means user need to go for initial spot check at the start of a user session. So definitely that can create malicious system adversaries like hacking or stealing personal information. At the same time, medical test falsification can also occur. And facial recognition using intrusive video imaging has a privacy issue because it requires intrusive video imaging. Physiological biometric-based approaches are promising. However, it requires contact sensor, which is sometimes cumbersome. At the same time, it can be uncomfortable as well. So considering all this, Doppler radar-based respiratory sensing technology has several potential advantages. First of all, it's a non-contact measurement. Then it's unobtrusive and comfortable. At the same time, there is a less privacy issue because no imaging technology is required. Now, I will move a little bit faster here because as Professor Lubicki's group has been working on this for a long time. So The basics of this particular sensor technology is it sends basically radar sends an electromagnetic signal towards a human subject or target. Then when the signal is being reflected, basically its phase changes, and the phase change of that particular reflected signal is directly proportional to the tiny movement of the chest surface due to the cardiorespiratory activities. So as I mentioned, the basic principle is like phase change of the reflected signal. There are some basic mathematical equation like transmitted signal can be represented as a T, where reflected signal phase shift occurs due to the tiny movement of the chest surface. And in our system, when the signal is being reflected, basically we multiply that reflected signal with the local oscillator version of the signal, and that gives us the in-phase channel signal. And we also, in our system, the system also multiplies that particular reflected signal with the 90-degree phase shifted version of the signal. So that gives a quadrature version of that particular signal. So from our system, we can get two channel signals. One is in-phase channel signals, another is a quadrature phase shifted version of the signal. And from there, what we can do the IQ plot that basically gives the space-time data. And if there is a periodic motion, that forms an arc. And from that arc, basically we can estimate the center. At the same time, radius can also be estimated. Now, when there is a periodic motion, basically the radius would be fixed and it would be constant. And if there is a sedentary respiration, if there is any kind of random body movement or any kind of fluctuation, at that point the arc could be a little bit distorted, and at the same time, the steady radius will not be maintained. So now how to extract the breathing rate and heart rate related information. So once we get the time domain channel signal, basically we do the linear demodulation. One is principal component analysis or eigenvalue decomposition of that particular two-domain channel signal to extract the maximum chest displacement information. Then we do the arc tangent demodulation also as well to extract the angle information from this IQ plot. And then we can take the FFT of that demodulated signal. So that gives us the peak of that particular FFT, gives us the breathing rate of that particular person. At the same time, by doing filtering, extra filtering, we can also extract the heart rate information as well. Now, let's have a look what happens when a person moves his limb. So here in the figure, the person is first fairly static, and we see the breathing signal going up and down, but when he moves their arm right before 1 minute mark, which results in this random variation in the signal. So what you can do, basically we can do the periodicity test and we can eliminate that particular fluctuation, and we can just focus on the periodic part, and then in that way we can extract the breathing rate and heart rate related information from that periodic portion of the signal. Now the question will come in our mind that what is the basic motivation of this identity authentication technology? As I already mentioned that we are trying to recognize people using radar signals. So it has been proven in various clinical investigations that different people breathe in different way. So their breathing pattern variations might occur in terms of their ventilatory variables or airflow profile. It may be occur in terms of their breathing depth, breathing energy, or sometimes it might be their respiratory rate. In addition to that, each individual has a different physical size and shape of lung, as well as different rib cage and abdominal muscle strength that contributes to the variation in breathing pattern. And it has also been quite clear that cardiac motion basically consists of contraction and relaxation of both atria and ventricles. So maybe cardiopulmonary motion may be an unique identity marker as well due to differences in physical size, shape, and muscle strength. So here we are proposing non-contact continuous identity authentication technology that basically consists of backscattered RF signal, which can carry body motion information. From that particular body motion information, we can extract the breathing rate and heart rate related information, as well as some unique pattern associated with it. And one of the potential advantages is that no imaging technology is required at all. At the same time, we can measure health status because breathing rate and heart rate can also be extracted from our system. Then we started looking at what people tried before in the literature to do this type of identity authentication. We found that people attempted before, and in literature, most of the attempt was focused on just single subject experiment, and that was limited to single subject measurement. But in practical environment, maybe in home sleep apnea testing or airport security system or automobile industry, there is a high chance of presence of multiple subject in front of the radar system. So when there is a multiple subject present in front of the radar system, basically it gets a combined mixtures of breathing pattern. So when it gets the combined mixtures of breathing pattern, it's interference of respiration pattern. So we started looking at this research question to understand better of the system. So can we still identify people when there is a presence of two subjects in front of the radar system? So to answer this question, definitely we need to know how to isolate the respiratory signatures from their combined mixtures of breathing pattern. So in my comprehensive exam, I talked about two different approaches. One is a ICAZ algorithm, another one is a direction of arrival. So let's have a look on three different scenarios. In the first scenario, consider two subjects, they are well spaced, and let's say our radar system can have a beam forming capabilities. So when they're well spaced, basically radar can switch beam in certain direction, and in that way it can isolate the respiratory pattern of each individuals. But what would happen when there is a two subject present within the beam width of the radar? At that point, direction of arrival will break down. It cannot isolate the respiratory pattern. So we need another technique. We used ICAZ algorithm. And now consider another complicated scenario where one subject is outside the beam and two subjects are within the beam. So we need to know how to switch between two different techniques. So here we are proposing SNR-based intelligent decision algorithm, and I will describe in details about it in my next slides. So before that, we also focus on, for this particular radio-based identity authentication system for one particular application, that's home sleep apnea study. Now the question will come, why home sleep apnea study? So we found that 50 to 70 million US adults suffer from a chronic sleep disorder, and 25 million US adults have obstructive sleep apnea, which causes daytime fatigue, high blood pressure, at the same time other medical conditions. So traditional method of screening OS is a polysomnography, where patients need to go to a dedicated sleep laboratories, and he need to go through that test in a sleep center coordinated by sleep technicians, which is sometimes a cumbersome. At the same time, it can be a mental torture. So home-based sleep study is gaining attention because it basically involves the use of sleep study machine in home environment, and patient can do that by their self-administration, and it's much more comfortable. At the same time, it's less expensive than polysomnography. But there is a one concern about that: data falsification can occur during this sleep apnea testing, and we found that there are some potential job holders like pilot and driver. They try to make sure that they don't get tested positive for this type of test because they are afraid of their potential job loss. At the same time, they are concerned about their insurance premium because they need to go for some restricted stimulant medication. So prior research to prevent data falsification mostly rely on fingertip sensor to maintain the integrity and authenticity of the sleep test results. However, unfortunately, attachment of sensor is always a cumbersome. At the same time, it's uncomfortable, and it can also change the sleeping pattern as well. So in our previous research effort, we already demonstrated that radar can recognize different sleep apnea events like apnea, hypopnea events can be detected without attaching any sensor to the body. So radar remotely can do that. Now in this particular research, we want to focus on radio-based identity verification system can also be integrated with the in-home sleep study machine to make this chain of custody process much more comfortable. At the same time, it shouldn't be that much cumbersome. So we are proposing a system that's called MASCOT, Modality Switch Compliance Tracking Protocol. So it starts when the patient first visits a doctor to obtain the test authorization. During the visit, basically, doctor attaches a chest band sensor to the patient, and then that particular chest band sensor links to the OSA app to initialize compliance tracking. The sensor continuously records the patient's breathing pattern when it is attached, and at that time, all the breathing pattern is stored in the tamper-proof storage media. Once the patient came back to his home and being ready for the test, at that point, the patients need to do some modality switch. So here we are proposing there are two different modality. One is a chest band sensor, another is a millimeter wave radar. And in between them, the app, initially there is a connection between the chest band sensor and the sleep apnea app. So when the app broadcasts a modality switch message to both the sensor and the radar, allowing the two to bootstrap a shared key based on their current breathing pattern, at that point, basically the chest band sensor applies AES and GCM key to compute an authenticable cipher text of the compliance data, and then it upload that particular data to the OSA app. Then the radar leverages the key establishment process to identify the patient and starts the OSA test by recording the multiple OSA related vital signs. So at that point, patient can take off his chest band sensor and radar can take care of rest of the screening technique. So during this chain of custody, he doesn't need to wear any kind of like chest band sensor in during this sleeping environment. So it might happen that patient need to go outside, or for any kind of emergency, he may need to visit restroom. So at that point, there will be another handoff will take place. At that point, basically, millimeter wave radar will have two different data set. One is a compliance tracking data set, another is the OSA screening data set. Again, that handoff will take place, and it will upload all the cipher text to that particular app, and then patient can go outside. So this type of handoff can take place multiple times based on the need. And once all this test is done, on the next day or the following visit, the doctor will look into the compliance tracking data set, and he or she, maybe the medical technician, will decrypt all the data set and try to see how closely that matches with the compliance technique to make sure that there is no data falsification occurs. So during that mascot design, we also considered some adversary model. So we can divide our adversary model in two ways. One is a mix-up and surrogate scenarios. Another is a eavesdrop and spoofing. So mix-up and surrogate is a very common scenario. The patient may follow his or her daily routine and share the bed with his partner. And during that time, there is a chance of mixture of two subjects. So presence of two subjects will create the interference of respiration signals. So we need to isolate that respiratory pattern. At the same time, it might happen that the patient may surrogate the test. He or she may like substitute another participants. At the same time, he may use some robotic phantom mover to mimic that breathing pattern. Apart from that, our system can do some extra work. That's eavesdropping and spoofing. So patient may eavesdrop the wireless communication between the sensor radar and the OSA app and seeking to evaluate the data records before the doctor examines them. So a CQ radio-based identity authentication is required. At the same time, our distinct features of our adversary model is patient himself is acting as an attacker. During this adversary model, we assume that radar and chest band has a temporary storage spoof capability. At the same time, they are capable of computing some cryptographic algorithm. Now I will mostly focus on the mix-up scenarios. So for this particular research, initially I will focus on mix-up, then step by step I will go into the other adversary models. So as I already mentioned, that when there is a presence of two subjects in front of the radar system, basically it's the interference of respiration signal, and it's hard to isolate the independent respiratory pattern from their combined mixtures of breathing pattern. So we found that pyro research mostly focused on using direction of arrival estimation, which is basically estimating the angular location of the target and then switching the beam in certain direction. But however, it has a certain angular resolution limit, and system can be complex when the number of participants increase. At the same time, when the subjects gets much more closer, system cannot isolate their direction of arrival. So we needed some kind of low cost scalable hardware. At the same time, ubiquitous physiological monitoring need to be maintained. So as I already in my comprehensive exam, I talked about two different techniques, ICA-Z algorithm and direction of arrival. Here I will try to show that by integrating these two approaches, an intelligent SNR-based decision algorithm, which can track both the well-spaced subjects and closely spaced subjects quite accurately. So in our system, we are using 24 gigahertz monopulse radar that can estimate the direction of arrival. So here K is the wave number, D is the distance between the receiver elements, theta is the position of the angular location of the target, and delphi is the phase change of between two receivers. And from there, we can basically estimate their angular location. However, one of the problem is it has a certain resolution limit. When the subjects are at the edge of the beam width, basically it can estimate the angular location of the target. Whenever subject crosses that boundary, it cannot estimate their angular location. So we are using another technique, that's ICA-Z algorithm, which is basically blind source separation technique, which is also a kurtosis-based separation technique. And one of the limitations is it requires better signal to noise ratio, but we'll show that how we quantify both of the system's performances. And then we are proposing an intelligent SNR-based decision algorithm. During this algorithm development, basically we consider 4 different scenarios. In the first scenario, you can see that two subjects, they are well spaced. Basically radar can switch beam in certain direction. and we can isolate their respiratory pattern. In the next scenario, in the figure B, you can see that two subjects are within the beam and one subject is outside the beam. So when one subject is outside the beam, basically radar can switch beam in certain direction. However, when subjects are within the beam width, it cannot estimate their angular location. So we need some kind of parameter of the signal to switch between two different approaches. So we, in the figure C, we also looked into when they have a different position of the subjects within the beam width, can we still like isolate them? Then in the figure D, that's now we are investigating like how many people we can accommodate within one beam width. Is it related to their physical size or shape? So that's what we are investigating now. So for these three different scenarios, we are proposing SNR-based intelligent decision algorithm. The signal to noise ratio of the received signal at a certain range within the beam width can be calculated using the radar range equation as shown in a figure, where PT is the transmitter power, GT is the transmitter gain, GR is the receiver gain, and K is the Boltzmann constant, and L is the propagation loss formula. And here we use the Friis propagation loss formula to calculate that particular propagation loss. So during this algorithm development, basically we consider two extreme cases. Extreme cases means when the subjects are at the edge of the beam width and when they start crossing that particular limit of the edge of the beam width and they start staying within the beam width. So we did that experiment from radial distances 1 meter to 3 meter for two different boundaries. One's boundary when subjects are within beam width and another boundary when subjects were at the edge of the beam width. Then we try to understand, is there any signal to noise ratio differences between these two boundaries? So during our simulation, we found that for different radial ranges, due to the change of propagation losses, basically its signal to noise ratio changes. At the same time, due to the antenna array gain differences, we can see that there is a 6 dB differences in between the two positions. So that particular signal to noise ratio differences helps us to understand estimate their positions. At the same time, we did that experiment in an anechoic chamber, and we also found that their SNR differences at two different boundaries were close to like 5.8 dB or 6 dB. So based on that, we are proposing a decision algorithm that is developed to switch between two different techniques. One is ICA-Z algorithm, another is a direction of arrival. So what we do basically, after capturing and filtering the radar respiration signal, we found the phase differences between the two channel signals and SNR of the received signal. And based on our simulation and experimental setup, we created an SNR lookup table for equidistant subjects at different slant ranges from 1 meter to 3 meter. And if the SNR of the received signal crosses that particular threshold limit of 6 dB from the maximum SNR at certain ranges, and phase difference between two received signal is higher than that functional limit of 100.5 degree, then we use the ICA-Z algorithm. On the other hand, if the SNR of the received signal is less than the threshold limit and the phase difference between the two receiver remains within the functional limit of our radar system, then we use the direction of arrival estimation, and we can switch the beam in certain direction and we can use that DOA. And we did that experiment in an anechoic chamber where two subjects were seated in a control environment. They were in a seated position. Also, they were using the reference chest respiration strap monitoring sensor as well, which acts as a reference signal. So here I'm showing the angular discrimination limit I'm talking about. So we calculated the angular discrimination limit based on their sidewise distances, where radial distances we calculated from the radar to the in the front direction. So here is some results from when subjects are well spaced. Here you can see that the capture signal for each subject was filtered using the finite impulse response filter in an order of 1000 with a cutoff frequency 10 Hertz. Then we measured the phase differences of the two receiver channel signal. If the phase differences remains within the functional limit of, as I mentioned, then we can estimate their angular location. Then we switch the beam in certain direction. And after estimating their angular location, after switching that beam, basically we do the FFT of that switch beam and the FFT of the chest bell signal. And here you can see that in the figure B, the blue line shows the beam switched channel signal, and red line shows the chest bell signal, and that closely matches. And then we did the experiment when subjects are closely spaced. So for closely spaced, let's say two subjects, their angular discrimination limit is 0.4 meter, and they are at a radial distance of 1 meter. And here we also looked into two different parameters. One is the SNR of the received signal, and another one is their phase differences. So here you can see that IQ plot, which is a basically constellation diagram that is much more distorted. And then we take their FFT, and in the FFT we can see that there is a two dominant peak that also gives us an idea that there is a presence of two subjects in front of the radar system. So here is an SNR of that particular look at that particular combined mixtures of signal. And then we looked into the SNR lookup table based on their different positions within the beam width of the transceiver. As the SNR is within that 6 dB threshold limit, then we did the linear demodulation of that particular two channel signals. And that signal was mixed with the random noise and mixing matrix. And then using the ICZ algorithm, we separated the independent respiratory pattern. Here you can see that the red line shows the separated source signal, whereas the blue line shows the chest bell reference signal, and they closely matches. Now, after doing that experiment, we try to quantify the performance of that particular proposed ICZ algorithm. So we did that experiment from radial ranges 1 meter to up to 3 meter, and for different discrimination limits. Here I'm showing that the first result shows when subjects are at a slant ranges of 1.5 meter, and the next diagram shows when subjects are at a slant ranges of 2 meter. So in addition to decomposition of the signal, what we do basically, we calculated the mean square error and cross correlation coefficient for the separated source compared with the chest belt reference respiration signal. And as I already mentioned, that we selected two different angular discrimination limit. At one limit, subject is within the beam width, and at another limit, subjects at the edge of the beam width. Then we try to see how their mean square error with the reference respiration strep signal and their cross correlation coefficient changes. Even at 3 meter, when subjects are at the edge of the beam width, we can see that their cross correlation coefficient is like almost 0.77. The reason behind is that when subjects goes far away due to the path loss, their signal to noise ratio is being affected. And at the same time, ICZ algorithm performance also degrades. So then we try to quantify the estimation accuracy of direction of arrival. So for quantifying the performance of estimation accuracy of DOA, what we do basically, as I mentioned, that when the subjects are well spaced at the edge of the main beam width of the radiation pattern, then we can employ that particular phase comparison monopulse technique to estimate their direction of arrival. And the estimation accuracy, you can see here at slant ranges 3 meter, we are getting like almost 81%, where for at 2.5 meter, we can get like almost 73%. So when two subjects are closer to the sensor, there is a higher chance of probability experiencing multipath. At the same time, we found another dominant source of error is a grating lobe. Grating lobe occurs when the antenna element spacing is of a transceiver is greater than half of the operating wavelength. So as the antenna element spacing here was like almost 13.77 millimeter of the radar transceiver we used, and operating wavelength was like 6.25 millimeters. So what happens when this type of functional limit occurs, basically they try to generate a lot of side lobe in between the main lobes. So after crossing certain ranges, it can show better estimation accuracy. Like after crossing 1.5 meter, the accuracy starts increasing. So then we try to quantify the performance of our proposed algorithm with the reported literature results to see how our proposed algorithm performance varies. So here you can see that basically after separating the respiratory pattern, we compared the respiration strep signal, how closely that matches, and then we do the FFT of that particular separated source signal and that reference respiration strep signal. And then we try to quantify the performance of our proposed system. We found that in literature, like most of the reported attempts just focused on for this type of multi-subject scenario is based on frequency modulated continuous wave radar. In our case, we are using CW radar. So CW radar has a different advantages because it's simpler in architecture. On the other hand, FMCW, it can estimate their range information. So let's say two subjects, they are in a different bin. When they're in a different range bin, basically by selecting their range bin, we can isolate their respiratory pattern. However, all the FMCW radar has some angular discrimination limit and due to the antenna array resolution limit. So we found that none of the system in the literature can solve that particular problem to isolate the respiratory pattern when the angular discrimination limit is less than 1 meter. In our case, our proposed system and algorithm basically helps to resolve this antenna array element resolution limit, because it uses DOA. At the same time, it uses ICAZ algorithm, because when DOA breaks down, ICAZ algorithm can take care of that particular portion. So here I'm trying to show the accuracy comparative analysis of our proposed system with the other reported literature results. Here you can see the black line shows the hybrid method we are proposing, and the blue line shows the ICAZ method. Here you can see that when the subject's angular discrimination limit is less than 1 meter, basically ICAZ algorithm performs better because subjects are within the beam width and signal to noise ratio is very high. However, at that point, DOA doesn't perform well because it cannot estimate within the beam width when the subjects are within the beam width of the radar. But when it starts crossing the 1 meter, it can estimate their angular location of the target. And then we basically manually switch the beam in certain direction to extract their respiratory pattern. And in that way, our proposed system can also estimate their breathing rate and heart rate even at angular discrimination limit 0.4 meter. And it can show an accuracy of always above 93%. So it outperformed than other reported results. So once we understand how to isolate the respiratory pattern, basically we started looking at radar-based identity authentication system for multi-subject scenarios. So as I already mentioned, the radar-based identity authentication system is basically analyzes the backscattered RF signals. So our proposed identity authentication system consists of four different components. One is basically the radar that basically captures the respiration pattern. And if there is a multiple subject present, as I already described, ICAZ and DOA can take care of that. And additionally, once we can separate their respiratory pattern, basically we looked into their features. If there any kind of unique feature remains within them to identify them. So apart from that, we also used machine learning classifier we also integrated the machine learning classifiers with radar system. And we have another aspect of this project. There's a security protocol, and I'll talk about in details how to handle spoofing and eavesdropping attack. Now, let's have a look what are the extracting breathing dynamic related features. As I mentioned that we extracted 11 different respiratory features, among them breathing rate, average maximum peak distance, minimum peak distance, then the standard deviation of the maximum peak, minimum peak, breathing depth, and spectral entropy. Those are very common features. However, we found some strong features that like remain unique for different participants. One of them is a dynamic segmentation, inhale area, exhale area, and inhale exhale speed. So now how to find that hyper features? The first hyper features, we are looking at the breathe ratio. So what we do basically, we took the 30% to 60% amplitude of the radar captured respiration pattern, and then we make the trapezium of the 4 different points in an inhale episode and exhale episode. And then we took the area ratio of that, both of that particular inhale and exhale episode. And that basically also tells us how one initiates the next cycle of breathing pattern. We found that this type of breathe ratio remains constant when subjects are in a sedentary respiration pattern. However, we did some of the experiment where after performing post-physiological activities, we found that their breathe ratio changes. Then their exhale area or inhale area remains constant. So we started focusing on to make sure that our system can have multiple features. And here inhale area and exhale area also represents the aerobic capacity and oxygen flow pattern, like how much oxygen can be absorbed. And after a short excursion, we found that people try to make sure that more oxygen is absorbed. So that's why their exhale area changes significantly. So for doing that, we try to improve that particular area ratio features. For improving that, what we do basically, after separating the independent respiratory features, we use their peak search method to find local minima and maxima point within that particular segmented portion of the signal. And after finding the peaks of the minima and maxima, we create an array of the 2 consecutive maxima. In between there is a 1 minima. So then we do the triangulation method in between 2 consecutive minima and 1 maxima. And that triangulation method, we calculated their inhale area and exhale area. And within each triangle, we can also calculate their inhale speed and exhale speed. So these 2 features, we found that for most of the participants was quite unique, especially these 4 features like inhale area, exhale area, and their inhale speed and exhale speed. And also the breathing depth sometimes remains quite constant. So the inhale and exhale area basically represents two cardiac phenomena. One is illustrates the ventricular contraction state. Another one is represents the ventricular ventricular filling state. So different, it might may happen that different people might have different breathing depth and airflow profile due to variation in cardiac movement, which will affect the area of that particular segment as well. Now, we did that experiment for 20 different participants and for different days. Here I'm trying to show that, let's say subject S, here it's an inhale and exhale area of a subject S, and different episode can also remain their same inhale and exhale area. Similarly, another participants here, you can see that they're significantly different than the inhale and exhale area of subject S. So here I'm showing the 6 different participants. If you look at the graph here, you can see that their breathing depth and their inhale and exhale area for 6 different participants is significantly different, where subject C shows a better inhale, higher inhale area, exhale area. At the same time, it shows the better breathing depth, higher breathing depth as well. And after extracting all these features, hyper feature set, basically we integrated the machine learning classifiers with our system. So we integrated 2 popular classifiers. One is a k-nearest neighbor, another one is a support vector machine. And in our dataset, basically we use the 60% dataset for training and 40% dataset for testing. And from that experiment, we found that SVM quadratic kernel outperformed than other classifier with an accuracy of 97.5%. Here is a confusion matrix. Here in the x-axis, I'm showing the predicted subjects, and y-axis is the true subjects. And diagonally, it shows the accuracy of the different classifiers. So from here, you can see that the subject 6 and 7, we found that they have some overlapping features. So sometimes due to the overlapping features, there is some misclassification occurs. Other than these 2 subjects, most of the subjects accuracy was always above 91%. So overall accuracy is still quite reasonable. So then we try to make sure that in our particular used machine learning classifier, there is a no underfitting and overfitting is occurring. So we looked into their learning curve. Basically learning curve shows the validation and training score of an estimator for varying number of training samples. If you look here, the blue line shows the training score and orange line shows the cross validation score. And with the training sample example, when the training example increases, basically the training score closely follows the pattern of the cross validation score. So it doesn't crosses that particular cross validation score. So we can quite sure that there is a no underfitting and overfitting occurring. So then we started looking at one of the security aspect of this particular project. So in security analysis, basically entropy is considered as a measurement of uncertainty of the system or unpredictability of the system. And for security analysis, we use this for entropy analysis, we use this Shannon formula, which is a very common entropy formula. So what we do basically for calculating the entropy, we took 3 different matrices. One is the radar combined capture signal, then we take the eigenvalue decomposition of that capture signal, and then we took the ICA, independent component analysis of that particular signal. And then we encoded the data with 4 to 8-bit binary vectors, which corresponds to basically 16 to 156 bins. And within that particular bins, we try to calculate their probability distributions of all samples within the encoded data bit bins. And then we do the normalization. And after normalizing each sample probability distribution, we took the sum of their entropy, both for FFT magnitude and for the phase informations. Here you can see that when the number of encoded bit is 4, theoretically we should get the entropy should be around 8, theoretically using the Shannon entropy calculation. In the left diagram, you can see the raw data is still for encoded bit 4, we are getting like 3 bits. So almost like half of the entropy is missing even in a raw data. And after doing the filtering, we see their entropy is like degrading. At the same time, when we are increasing the encoded bit, basically we are increasing their uncertainty as the number of encoded bit is increasing. So definitely entropy should also increase with the encoded bits. So after ICA data, we looked that their entropy was almost like 3-bit, which is for in terms of security application is vulnerable to any kind of attack or any kind of eavesdropping. So we need some kind of secure protocol technique to combat this type of attack. So here before what protocol we develop, before describing that, I will talk about the research challenges for eavesdropping and spoofing during device pairing. As we are pairing two devices, one is a chestband sensor, another is the millimeter wave radar. So secure device pairing is a process that bootstraps secure communication between two physical devices. And we want to make sure that during that pairing, no other attack can take place. So here I'm trying to show that the human user Alice is trying to pair the computer A with the phone E. And here in the phone E, there is a malicious app that is controlled by the attacker Mallory. So the malicious app is basically able to spoof the pairing user interface on the phone at Mallory's command. So the attacker also has a third device B, which is hidden from the user's view. And attacker's goal is to pair Alice devices A with the third device B. So this type of insider attack can take place during device pairing. So we need some kind of protocol that can handle or that can combat this type of attack. So we developed a key evolution protocol. As I already mentioned, that we are proposing a system that's basically modality switch compliance tracking system, which can do the OSA test compliance tracking based on the patient's identity, based on the patient's current breathing signature. At the same time, it can switch between two different modalities, tracking modalities, switching between two sentinels. One is the chestband sensor, another is a millimeter wave radar. So the core of this mascot system is a three-party key evolution protocol, which allows two sentinels A and B to securely evolve a shared key based on their current breathing pattern. So we introduce fuzzy commitment scheme during this protocol. So here, this three-party key evolution protocol starts when basically the app broadcasts a modality switch message. The modality switch message is represented here. You can see H, which is basically cryptographic hash function. I-1 is the initial key, and TSTR is the timestamp of the breathing pattern, starting point and ending point. Once that key is shared between the two devices, basically both of the devices, based on their modality, they can convert that particular timestamp breathing pattern into a breathing fingerprint. Here, phi is the breathing fingerprint function, and I will describe how breathing fingerprint function will work in my next slides. And once that breathing fingerprint is generated, basically it can encode that particular fingerprint using the Rich-Solomon encoding function or the fuzzy commitment scheme. During that encoding, it can generate the key opening value, and it can share that particular key with another device, which device is paired. Let's say is modality switch is taking place from chestband to the millimeter wave radar, then that key will be shared from the chestband to the millimeter wave radar. And based on that key, it will also compute that, it will also generate that breathing fingerprint. And using Rich-Solomon encoding function, it can also decode that particular key, and it can also verify that whether there is any kind of discrepancy occurs during that key derivation. So apart from that, we also introduce physical jamming during this device pairing. I will talk about that. And if two key matches, basically an acknowledgement signal will be sent, and device modality switch can take place at that point. So the goal is to each and every time the key needs to be leveraged by the former sentinel to protect the authenticity and integrity of the compliance and screening data being uploaded to the OSA app during modality switch. Now I'll talk about how fingerprinting function will work. As I mentioned, that phi is a fingerprinting function. Once the sentinel obtains that breathing pattern using the radar, basically it will convert that breathing pattern into a binary code word. So binary strings should look similar in Hamming space for one person. At the same time, it should preserve the uniqueness of breathing dynamics. So you can see here that the breathing fingerprint, from the radar, basically we are getting the continuous signal. So here we are proposing the multiple level crossing sampling. Let's say when the breathing pattern is crossing the particular Q plus level, at that point it will generate the code 10. If it crosses that, it is less than Q minus, it would be 01. If it is in between these two levels, it would be 00. So in that way, we try to quantize the breathing pattern. And from our initial data set, we can also know the thorax motion, maximum chest displacement information. At the same time, we know the maximum breathing rate and heart rate information of 20 different participants. So therefore, we employ 10 level crossing quantization branches with a quantization step size 0.05 centimeter at a sample rate of 10 per second to preserve the to preserve the fine grain respiratory motion of the breathing fingerprint. So after that, we do the physical jamming. So what happens? The on-duty sentinel, which will take that particular modality switch, convert that particular message into OFDM symbol and broadcast that 2 copies of each symbol back to back towards the receiving sentinel B. And during the transmission, a physical layer jamming protection is also enforced from B to prevent any kind of insider attack by any kind of eavesdropper or any kind of insider. So what is physical layer jamming protection mean? So here we are proposing, or we are integrating, we are not proposing, basically we are integrating that physical layer jamming technique that ensures an eavesdropper cannot even demodulates a wireless signal that is not intended for it. That means device A is sending a signal to device B. So another device cannot get that particular signal because it cannot demodulate that particular technique. So it would be channel independent technique. At the same time, during this technique, sender repeats its transmission. So as shown in a figure here, you can see that each sample in this repeated transmission, the receiver randomly jams either the sample in the original transmission or the corresponding sample in the repetition. Since the eavesdropper does not know which signal sample is jammed and which one is clean, it cannot correctly decode that particular data. And in contrast, the receiver knows basically which particular sample is jammed. Thus, the receiver can pick the correct samples from the signal and repetition and rearranges them to get a clean signal. And then it can decode using standard method, as I mentioned. So in that way, basically, we can also protect any kind of attack by insider attack or any kind of eavesdropping. So once all this method is integrated, we are trying to empirically evaluate the performance of our proposed system by using our laboratory prototype of the modality switch compliance tracking. So we use 2 different radar module, as I already mentioned, about 24 gigahertz KMC4 radar. Then we also use the BVOX 24 to 31 gigahertz millimeter wave beamforming radar. And we also use the piezoelectric respiration transducer. So here for experimental setup, basically we empirically evaluated their performances, both for single subject compliance tracking experiment. We did that experiment both anechoic chamber and outside the particular laboratory environment as well. So the subjects are between basically the ages of 16 to 35, and they were way between like 40 to 85 kilograms, and none of them have no prior history of heart disease. And for the mix-up and surrogate scenario, basically we randomly pair 2 subjects, and both subjects were asked to each wear a chest band and lay down under a millimeter wave radar throughout the experiment without knowing which subject is basically the patient. And for surrogate scenario, like one subject were wearing the patient were wearing the chest band sensor, and another patient was like lying down under the millimeter wave radar. And for validation of eavesdrop and spoofing, basically we used a Bluetooth sniffer where packets were transmitted by the OSA app and chest band using Bluetooth, and then host code record that packet during each modality switch, and then we do the offline analysis. And for spoofing, basically a pre-coded data was transmitted from the radar system towards the pre-coded data was transmitted from the Bluetooth sniffer towards the app to make sure that any kind of like falsification can occur. So here is the results for mix-up scenarios. So we randomly pair subject, as I already mentioned that. So here is the result of the 2 channel signals, and you can see the constellation plot diagram. Then we do the linear demodulation, and then we use the ICAZ algorithm, as I talked about it a lot. So after separating their respiratory pattern, basically we can extract their hyper features or their normal features as well, like breathing rate, heart rate, at the same time inhale and exhale area. Once that hyper feature set has been extracted, basically we converted that breathing pattern into a binary code word using the multiple level crossing sampling. And then we looked into their Hamming distance. So we looked into for measuring the performance, we looked into their Hamming similarity per bit between fingerprints of the same subject with different modalities. Like same subject were wearing the chest band sensor, and they were also taking the radar measurement. And we did that experiment for different subjects in different modalities. Here is a result where x-axis shows the capture duration, y-axis shows the breathing fingerprint similarity. So here we can see that Hamming similarity per bit between fingerprints of the same subject for different modalities for 6-second capture duration is around like 63% from mean of the box plot. And if the capture duration starts increasing, you can see that they are the reduced mean and variance is also their fingerprint similarity is increasing. So that's happening due to the capture duration time, extension time of the capture duration, which allows repeated measurement. At the same time, the breath cycle is also increasing with the repeated measurement. Then we looked into Hamming similarity per bit for different subjects. Like one subject was wearing the chest band, and another subject was lying down in front of the radar system. And here I'm showing that even the capture duration increases, the fingerprint similarity for different subjects for different modalities is not like less than 5% always, even the capture duration increase. So that also tells us that the proposed system can handle mix-up and surrogate scenarios together. And then we also analyzed for changing different slant ranges, like from 0.5 meter to 3 meter, how their breathing fingerprint similarity matches with the chest band stem. And here you can see that when the slant ranges increases, basically the fingerprint similarity degrades because the signal to noise ratio is degrading due to the path loss. And that's also affecting the extracted hyper feature set similarity with the breathing fingerprint similarity. And that's also affecting the Hamming similarity per bit. Then we also looked into the performance for, as I mentioned, that two adversarial setting. One is the surrogate, one is the eavesdrop and spoofing, and we are handling that using the fuzzy commitment scheme. So we looked into the generation time and reconstruction time based on their error tolerance bit. Here you can see that when error tolerance bit is increasing, basically the generation time is decreasing. At the same time, we looked into their reconstruction time, how long it can take to retrieve that particular key. In the graph, you can see that even we take the error tolerance bit 8, still we can generate key less than 10 seconds. At the same time, we can also reconstruct key like within 14 seconds as well. Then we also try to understand like what would be the best error tolerance bit for that Rich-Solomon encoding function. Here you can see in the second graph, when the error tolerance bit is increasing, basically the false positive rate is also increasing due to the randomness of the error tolerance bit, and false negative rate is decreasing. So we try to make sure that the error tolerance selection of error tolerance bit is such that we can get the optimal false positive rate, at the same time optimal false negative rate. From the graph here, it's clear that error tolerance 8-bit works best for our proposed system. So here is a overall performance of our proposed system against 4 different adversarial settings within the existing single modality switch system. Here in the graph, we use 2 different metrics. One is the for mix-up and surrogate. Basically, we use the protocol sensitivity. It was calculated based on the true positive rate, and the specificity was calculated based on true negative rate in identifying any kind of intentional or unintentional identity changes. As I mentioned, that single layer modality switch is also can use the support vector machine with a linear classifier to detect the identity changes. So empirical results shows that merge scores are close to the single modality SBM approach for both of the scenarios, surrogate and mix-up. And for eavesdrop and spoofing, our metric was the bit error rate, and that was bit error rate was the aggregated bit error rate of the receiving sentinel versus the aggregate bit error rate at the attacker. And due to the application of the fuzzy commitment scheme, the key evaluation protocol allows a maximum of 27% bit error rate in the breathing fingerprint. So Rich-Solomon code is used to recover that key sold. So from 4 different adversarial settings like surrogate, mix-up, eavesdrop, and spoofing, it's quite clear that mascot performs quite well, and it can handle at the same time surrogate and mix-up scenarios. It can handle also the eavesdrop and spoofing attack. So in conclusion, radar-based continuous identity verification system has been evaluated for in-home sleep apnea testing environment, and we extracted highly distinguishable breathing dynamic related features. At the same time, we are proposing SNR-based decision algorithm to measure the concurrent respiration monitoring of multiple subjects by integrating 2 different approaches. One is ICZ algorithm, Another is the direction of arrival algorithm. Then an extensive secure and cryptographic protocol was integrated with the cardiopulmonary radar system to make sure that different attack scheme cannot take place. Like we also analyzed different attack scheme like eavesdrop, spoofing, mix-up, and surrogate. And we are also develop a modality switch compliance tracking protocol, which can switch between contact-based chest band sensor and the millimeter wave radar. So for future work, basically we are focusing to integrate our proposed system with the clinical study of obstructive sleep apnea. We also want to make sure that we can recognize people for different sleeping positions, like if people sleep in their back or side, still we want to recognize them. And we're also interested in integrating the deep learning and artificial intelligence with our system for automatic feature extraction. So before concluding, I would like to thank my advisor, Professor Victor, for being very helpful and nice. And without his support, basically, I wouldn't be able to come at this point. And I would also like to thank Dr. Olga for being very nice and helpful. She also helped me to revise a lot of my manuscripts. And I would especially like to thank Dr. Yao Jiang for helping me to work on this particular security aspects of this project. And I would like to thank the rest of the committee members like Dr. Aaron, Dr. Yelena for providing timely feedback and for replying email like quickly. And those who attended from different places of this world, I would like to thank everyone. With this, I would like to conclude. Thank you so much.
Thank you. Okay, so we'll have a little time here for questions and from the general audience, and then we'll conclude things and the committee will remain on task for more questions. So anyone from the general audience, I see there are a lot of questions here. So let's see, actually, no, I don't. That's the wrong column I'm looking at here. So you can either speak up or send something in the chat if you have any difficulty with your audio. But please, if you have any questions, please volunteer them.
Okay, thank you very much. My name is Ahad from Japan at this moment, but I am from the same department of Mahmoud in Bangladesh, University of Dhaka. So I'm a professor there and currently working at Osaka University in Japan. So it's a wonderful work, and I know that how both of you, helped him and supervised him excellently. So my question is about the ICA-JET and or DOA, direction of arrival approaches or algorithms. Over there, you mentioned in the maybe one of the earliest slides, 15 or in between 15 or 20, that ICA-JET separation technique to separate respiratory signatures. Would you please explain a bit more on this part? That
how it works?
Yeah. This part. Yeah. Thank you.
Right. Yeah. So I have some slide, like extra slide for that.
Okay.
So yeah, so that's a great question. Good question, I would say. Thank you, sir, for that question. So what we do basically, we use the independent component analysis JET algorithm. So it works based on kurtosis-based separation technique. So what it tries to find, basically, if you look here, sorry for I think this slide. If you look here, you can see that when there is a normal respiration pattern, it's a kind of non-Gaussian. But when there is a combined mixtures of breathing pattern, you can see the distribution looks like Gaussian. So what it tries to do, when there is a combined mixtures of respiration pattern, it tries to find the non-Gaussianity based on the kurtosis of the data samples. So for non-Gaussianity, basically kurtosis works in a way that you see there, when it's a non-Gaussian, you can see that here in the distribution that the Gaussian, there is not that much tailed on the both sides is a flat. Whereas on the other hand, when there is a independent respiratory pattern, basically you can see that its kurtosis, there will be some tailed on the right side. It's not like a centrally distributed. So for doing that, basically it follows these steps. First, we do it tries to find the orthonormal column, but by removal of the mean. Then it tries to calculate the cumulant, kurtosis of the data set. So based on the kurtosis, it can understand that some data set are either that particular data portion is a Gaussian or non-Gaussian. And based on that cumulant computation, it tries to extract all these cumulant, it tries to decompose all these cumulant metrics, and then it's do the like eigenvalue decomposition by doing the diagonalization of the eigenmetrics, it can extract that particular independent respiratory pattern signal from the combined mixtures. So does that answer your question?
Yes, thank you very much. May I just ask another query?
Sure.
Oh, okay, thank you. So it's about, I mean, the features. You mentioned that there's, I mean, better features or a hyper feature,
Right.
yeah, 6 or 7 features. So I don't know that whether these are all proposed by you or you considered from different papers, and number one. And number two is that how can you say that these features are very authentic or uh, very discriminatory? So
Right.
any I mean input on that? Yeah.
Okay.
Thank you.
So that's a good question, I would say. So I think before me, there was another student who worked on that. So I got that particular breath ratio feature. That paper is already published, I think, IEEE Journal of Emerging and Selected Topics in Circuit and
Oh,
System.
okay. I noticed that now.
Yeah. So in that particular paper, we already talked about that when for 6 different participants, it worked very well. Like it can identify 6 different participants almost like with an accuracy of 95% classification accuracy. But later on, like whenever we are doing some experiments where people are doing some physiological activities, we found that sometimes their bid ratio changes. So then for the next slide, if you look here, I think this that hyper feature is proposed by me, but we also see that some other paper, I didn't put that paper, they also did heart-based dynamics. Like they try to extract the heart-based dynamic features based on like 4 different points in a respiration segment. So it's quite close, but it's still additionally, I'm doing like triangulation method. And then I'm also trying to find like the inhale and exhale speed. And it shows like significantly different. And also we found the breathing depth. So some features we got from the literature and some features like we are also proposing. And right now our experimental setup is mostly for sedentary respiration pattern, but we started looking at like, let's say people are doing exercise, whether this feature will remain constant or it will change. So that's what we are now investigating. Like we have a data set for 6 different participants. They did some exercise and then they are taking this radar respiration measurement. So we are trying to integrate some extra layer with our proposed system now. So far, the result I showed is like just for sedentary respiration pattern, but I think that should be our next step.
Yeah. Well, wonderful. Thank you so much.
Thank you.
Are there any other questions?
Can I ask a question? Am I breaking out again?
Sure, but as a member of the committee, we'll ask him questions ourselves after I free up everyone else. So if you'd like to save it until then.
Okay.
Okay, so maybe we'll do that then. If there are no further questions, again, I'd like to thank Mahmoud for an excellent presentation. And thank you all for coming. I'm sorry we can't treat you to anything that we would normally do for a live exam afterwards. That's just one of the hardships of our times. But again, thank you for being here to support Mahmoud. And we'll now carry on after you all sign off.
Yeah, thank you. Thank you very much. It's wonderful. All the best.
Mahmoud, you might actually be able to selectively disconnect people as the host of this meeting. I'm not sure. I've seen that on some
right.
platforms.
So I'm then removing, like without committee member, I'm removing others then, yeah. I think, yes.
Oh, we've lost Yelena.
No.
You know, I was confused because Victor, you sent another link just for the committee. Was
Yes,
that
I did, because as host, at some point when Mahmoud is no longer joining us, I'm not sure that I can sustain the meeting. He might be able to hand the host over to, he might not. So I've added another.
I think now just committee and me, no one is here, I think. Yeah.
Right.
Yeah.
I'm just, it is, yeah.
Yelena's back on.
Yeah,
I know it's confusing. I just set that up because I know in the previous exam, we didn't dare have the examinee release his host position, and it was tricky. So this way, I think either he can hand me over as host, or we'll use that other link after we've asked some questions.
He can assign you as a host, I believe.
I think so. Most platforms, I think Zoom is one where he can do that. So we may not need that other link at all.
Mm-hmm. Okay.
Okay, so let's open it up to the rest. I know that Yao already had a question he was eager to ask, so I'm sorry I cut him off, but I wanted to save it for this stage. So maybe Yao, you could start.
Okay, so I understand that you are using ICA-J to achieve a superset resolution when you have multiple targets within the bandwidth, right?
Okay.
And based on our discussion, I see that ICA-J might be a little bit unstable when one of you experience large movement from the subject.
Mm-hmm.
So let's say that you have 2 persons.
Mm-hmm.
And they have a combined breathing mixture that is captured by your radar.
Okay.
And you can use ICA to separate them when they are not moving, when they're just standing there, being still, and have small movement in their chest, right?
Right.
And if all of a sudden one of the person actually, let's say, make a turn, and the ICA-J need to be recomputed. And by the time you recomputed the breathing pattern that belonged to the first eigenvalue might now move to the breathing pattern belong to the second eigenvalue after you do the recomputation, right? So I say you might have this kind of issue when you mix identity. So they have a swap issue, right?
Right. So you're talking about the participants will swap, or due to the.
So let's say that after your ICA-J, before the big movement, the first eigenvalue corresponding to a breathing pattern belong to subject A, and the second breathing pattern belong to subject B. And after the big movement, you may have a switch, right? So the first eigenvalue belong to subject B now, and the second one belong to A. So I think we have discussed that there are multiple techniques to achieve, to basically link the identity before and after the big movement. So my first question is, what's your thought on that? How are you going to link those identities?
Right. So before filtering, as ICA, I know that because ICA try to extract that the eigenvalue, it needs to decompose that eigenvalue. So before filtering, if there is any kind of, let's say, random body movement, probably in IQ plot or if we do the periodicity test, probably we can discard that part and just focus on the periodic part. That can be an option. And for ICA-J, I'm not sure here I'm used JET, but I found maybe there are some other improved technique like robust ICA and other improved technique. I'm not sure like they can handle this type of jump, because I'm not sure. Probably ICA-J will not be able to handle at that time. Misclassification may occur, yeah. But
so let's say that we implement a big motion detector that can detect the large movement.
Right.
And so because based on your presentation, we see that we can see there's a lymph movement which cause a big disturbance in your data capture, right? So let's say that we segment the breathing pattern into multiple segments, and you do the ICAJ for each of the segments, and you were able to basically extract individual breathing pattern. But now you have this issue to link those breathing patterns to the same patient, right? So will you be able to do that with your existing features?
I think then existing feature might be affected because we are considering for feature extraction, we are considering that inhale and exhale area. So I think at that point, the maximum peak point and minimum peak point will also change. So with this scenario, probably it cannot handle that, but by considering the segmentation technique, probably it can do that. But for experimental scenario, we mostly did that like in a sedentary respiration pattern in a seated controlled environment. But I believe like with the segmentation technique, if we can discard that random body movement, probably it will work.
Okay. And the last question. So in your opinion, let's say that we use this thing for security application where reliability is a big concern now. Do you think using ICAJ to achieve super resolution versus, let's say that we have a distributed radar system with multiple beams to separate the breathing pattern, which one do you think is more reliable?
I think DOA is a kind of reliable. However, it depends. Like if we want to implement this system for a scenario, like let's say subjects are well spaced, at that point, like switching the beam in certain direction helps us to make sure that no like combination of the respiration pattern is occurring. So I think DOA might be much more reliable, but there is a chance like you can see that the subjects may be closer. So we found that like DOA has limitation like the antenna resolution limits. So with answering your question, I would say DOA would be much more reliable. If we can make the beam much more like super resolution beam or very narrow beam, probably that would be better.
Okay. All right. Thank you.
I think the bar is a little bit lowered in this sort of authentication scenario where you can have a scenario where if you have multiple people, if you can see them with separate beams, separate radars effectively, great. If they're too close, you can use the ICAJ. In some cases, they can't help but be too close. That's fine. As long as the system's robust to this, it can say, yes, I distinguish the two and I'm fine. If it gets to the point where the system determines itself that it doesn't have a high level of confidence, it can deny the service and say you need to get further apart or you need to do something. It's the same thing. We've done this before with reporting medical diagnostics. It'll give you a number that it's quite certain is correct. And if the scenario gets to where it can't really read your heart rate, it can't really, it simply says, I can't provide that information under, this is not clear enough data. I can't provide that information. So that helps, picking scenarios out like that don't require necessarily 100% of the scenarios are compliant. It just will tell the user that I can't give you a number until the situation improves. Yeah. So I'll let others ask questions, and anyone else want to go next?
Can I ask a couple of questions?
Sure.
So if you go to slide 34.
34, okay.
Yeah. I didn't fully understand that graph.
This one? Okay.
Yeah.
Okay. So you mean this graph, right?
Yeah. Can you change it to the regular presentation view, because I can't read the graph.
It's pretty small on our screens. You're showing, you're showing the presenter view. or you could do this the slideshow. Just
if I increase it.
Oh, okay.
This will block. Yep.
Okay.
Okay, so the y-axis is the truth, and the x-axis is your prediction.
Right.
Yeah.
Right. So true is a y-axis and x is a prediction. Yes. And diagonally, it's like classifying. So here you see that, let's say subject 6. So you can see here diagonally is the classification accuracy, and it's a false positive, like 6% is counted as a subject 5 and 6% is counted as a subject 7. So overall false positive is 12%, and accuracy or true positive is almost like 88% for subjects. Similarly, other like subject 2, 95% is true positive, but it was misclassified as a subject 1, like 5%. So that's the false positive.
Okay. I think I understand this more. So then maybe I missed it. So what are the subjects? So you have, I mean, what are scenarios? So you always have three subjects at once, I guess?
2 subjects, not 3 subjects, for 2 subjects. And they were in a like control environment. They were like sitting in front of the radar system.
Okay, okay. So if you go back to your example of 6 being, you know, you're showing the error in the reading for 6. So that 6% false positive is when you're measuring subjects 5 and 6 at once.
Right.
And the other 6% false positive is when you're measuring subjects 6 and 7 at
right.
once. Okay. So, okay, but this is the classification accuracy for only the SVM, right? It's not for like the whole system.
No, so it's a, yeah, so we like, this one is just for probably mix-up scenarios when 2 subjects are present, like we try to see how classifier performs. But here, the hyperfeature set is just a number we put as a like analog number. But later on we did where we convert each of the hyperfeature set as a binary code word. And then we try to see like how their Hamming distances changes from different binary representation of that breathing pattern.
Okay, so maybe I missed that performance then. So if you look at the system as a whole, right?
Mm-hmm.
So it includes like the noise from your measurements and all of that, plus this classification accuracy effects, then what is the system accuracy?
So you mean the attack scenario accuracy, or so here, this one, I think probably this diagram. So here, what we do basically for surrogate and mix-up, we use the matrix as a like true positive and true negative, as I already showed from the confusion matrix. So you can calculate the sensitivity and also specificity or selectivity for surrogate and mix-up scenarios. But for eavesdrop and spoof, basically the machine learning classifier cannot handle that. So we need like different metric at that point, because
these are all in the where you're trying to screw up the system, right? So what about when there's just 2 people there and you're just trying to identify them?
I think that accuracy can be even within the SVM.
I think that for just 2 subject cases, that's the single modality.
Right,
accuracy,
single.
Right.
So
this one. That's basically the best case SVM can achieve.
Right, linear kernel. So that shows the.
So basically the idea here is, let's say that you have two modalities switching between each other. One modality is a contact sensor, that is the chest band attached to the patient. Then you have the millimeter wave also try to identify patients. And for single modality case, basically it's the breathing pattern, whether we can use the breathing pattern to differentiate people. And that is consistent with the SVM result. For multi-modality cases, that means when we have a switch from chest band to millimeter wave, and during that switch, we use that key evolution protocol to make sure that there is a consistency in terms of identity. So only if the chest band and the millimeter wave, they are monitoring the same person, they can jointly evolve that key. And in order to evolve the key, the idea here is if the breathing, let's say breathing signature, that the binary signature extracted from the breathing pattern, they are close in terms of Hamming distance. And because of the multi-level quantization method that we have, the Hamming distance, the closeness of the Hamming distance correspond to the Euclidean distance in the SVM. So they are equivalent. So when there is a modality switch, we compute whether this key evolution is successful or not to basically reject any potential identity switch. And that will lower the specificity and sensitivity a little bit because there is a potential of attack window when another person jumps in. So that leads to the results of a slightly lower in terms of the parameter. But the basic idea here is when there is a modality switch, the Hamming distance based the key evolution is algorithmic equivalent to an SVM classifier. That's basically the idea. So that gives the plus. Yeah, we're still updating that class for the error swapping and the spoofing, which will be basically based on the BER, the bit error rate during the transmission.
Okay, so I guess another way to put my question is that, if you have two people sitting in a room and you're just trying to verify the identity of the two people, and there's nothing bad happening, no one's trying to eavesdrop or pretend they're someone else, then what % of the time will you get an error? And it sounds like it's the same as the SVM error.
Right. Based on the classification accuracy, right? So we use the two different classifiers, KNN and SVM, and SVM performs better than KNN, and that would be the SVM, right? SVM output.
Okay, yeah, but
because we need.
I understand that the SVM error would be, I guess the current limit in how well it can perform, but that means there's no problems with any of the other parts of the system. Like everything else is working ideally. So
every like right for our experimental scenario, we did like most of the experiment when subjects are within beam width, and like we want to make sure that like they have a better signal to noise ratio. And we didn't do any other experiment, like let's say subjects are far away. Here, most of the experiment we did considering the like sleep apnea application. You know that in sleep apnea, like the participants may share the bed like closely, and it may be like 1 meter distance. So considering that, like I think the angular discrimination limit was around 0.5 meter, and they are within the beam width. So I would say we didn't investigate other aspect, like if they are far away, whether our system is like how much.
Okay, so I think I get it. So you're kind of making the rest of it as close as possible as you can to the ideal condition.
Right. Considering the sleep apnea study, right?
So I don't know if it's beyond the scope of what should be included in this, but I mean, should you, or can you make an estimate of, if this was deployed as a real biometric security system, you're not going to have people just always staying in the same place, right?
Mm-hmm.
So what would be kind of the real world performance that you would expect?
So for real world performance would depend probably based on the variability of the experimental parameter we integrate, but the experiment we did is a kind of control, but we also considering the real world scenario, like let's say two participants, they are sharing the bed like at a 0.4 meter distance. Even in a sitting in a like lying down environment, like we try to see whether we can like recognize them. So it depends like what particular application we are focusing and what particular specific like experimental scenario we are considering. So I'm not sure like how to quantify that performance. Like it may be variable based on the other parameters if I consider.
Yeah, I'm sure it is. But,
Mm-hmm.
It's a good question. It's a tricky scenario. We've looked before at people just like measuring their heart rate, and we had people, volunteers come in and read a book or watch TV or something like that. And so we were able to get 70% of the time they were sedentary enough that we can recognize this, so, over long periods of time. So we didn't do something like that for the authentication, but you can see why when you're looking at the best case of reasonably sedentary conditions, it's not that crazy. It happens a lot. It gets interrupted a lot, but so you'd need a system that can say, what can I tolerate? You've checked in, I know it's you. Every so often I have to be able to verify it's you. If that every so often breaks down beyond a certain limit, then it has to have a flag. But it's a very good point. That's an important part of the examination of the quality of the system. And I think Mahmoud did a little bit more in terms of the robustness when he was just looking at a single person, recognizing a single person out of a group before he started separating multiple individuals. But when he started separating them, it was always like under the ideal condition, what would happen?
Yeah, so I mean, I'm not asking you to go and do some experiments because I know that would be kind of beyond the scope of what you're trying to prove here. But Dr. Levecki and Dr. Borg-Levecki's group have done a lot of prior work. So, like Victor said, so if people normally move around or stay still 70% of the time, right? You can kind of use that as a baseline and say, okay, maybe about 70% of the time, there'll be ideal conditions. So you have that, and then 90% of that time, based on your SVM, you'll be able to accurately identify them. So that's, gets a little closer to what you can expect for the real world performance.
Actually, Mahmoud and I have discussed when we developed the paper on compliance tracking. Mm-hmm. And the reason that eventually we land onto this application, so it's a compliance tracking for sleep apnea test in order to prevent, patient fraud or data fraud, is for this particular scenario, the subject has to lay down. And being so it's more of a controlled environment compared to just generic, breathing-based alternative. So that was able to allow us to elevate the accuracy of it.
The sleep scenario was a good one because we've already shown you can do good medical diagnostics in the sleep scenario, and then on top of that, you will have to be faced with separating two people, which is another one of the strengths. But you'll look at kind of the most ideal case for separating the two people. Right. So it's a really nice way to step into this. And yeah, I'll actually, I don't want to ask I'll ask my questions last, but maybe Aaron, do you have further questions?
So I have one more question, and this one has much less to do with what you actually did. So you know, you might not know the answer, but so you've done a lot of analysis on breathing, and you know, you're able to detect all these different patterns within breathing. So do you think this has some relevance to treating COVID-19?
Yeah, absolutely. I think we already, for COVID-19, I would say, yeah, it's one aspect of COVID-19 can be like tracking different like respiratory pattern, maybe their different respiratory conditions we can track based on like changing their variability of their breathing pattern. And one of the advantages can be like it's a non-contact. So you know that like for identity authentication, like this particular technology can be helpful because most of the out to the market, like all are like contact sensor based. And for COVID related, we already started like for our, I think I put one slide here. We already
yesterday you just had a paper accepted. That
right. We have a one paper accepted in, I think, APMC, where we did like experiment where like we told the participants to mimic different kind of breathing, like normal, fast breathing, slow breathing. And I tried to see like how ICA-J algorithm performs. So we found that when people try to like mimic the fast breathing pattern, there was a much more like motion. So motion artifact was too much. At that time, we found the ICA-J algorithm perform degrades. Then we also integrated some other techniques. So yeah, that paper is recently accepted in APMC. So we started looking at the diversity of different breathing pattern to recognize people also.
So how fast is fast breathing compared to normal breathing?
So fast breathing, I think it should be more than, I think, 0.5 hertz. So almost like 25 breaths per cycle. More than that, I think 30 breaths per cycle. Yeah, 30 would give that like almost close to 0.5 hertz, I think. Yep. So here we told the participants to mimic this type of like breathing patterns. So then we also use the chest belt to see like how it changes. We can see the variation in also in IQ plot, like it becomes much more distorted with the variation of their pattern.
I think that the first and foremost thing you want to see is if someone goes into a shallow but rapid breathing pattern. And that's what the body normally does if you're not getting enough oxygen. That means if you can't take a deep enough breath, you take more shallow ones. So that sort of trend. And it's, I think, over 20 breaths or under 20 is kind of a breakoff point. And then how deep those breaths are. So nobody's got a magic COVID pattern that fits everybody. But there are some pretty good indicators that are what people have to go by anyway. If you go up to the doctor and they have a look at you, they're going to do that in a less quantitative way. So it does have potential there. And yeah, I thought they managed to come up with a pretty quick explanation of how that might work in this paper.
Okay, thank you.
Thank you.
So one of the things that happens here before I ask, you have to recognize that when ICA-J is performed on the signals, it's a little different than having two radars or a DOA in that it's a filtering process. And it's sort of like what we've done. Nobody's asked about it yet, but a good question would be about what about using heart rate? And in general, I'll tell you why I haven't pushed them to do that is when you see both heartbeat and breathing, heartbeat is much smaller. And depending on how you breathe, many people have harmonics from their breathing overlapping with the harmonics in the heart pattern. So once we filter breathing in order to see the heart pretty well, we're not looking at the full heart signature. We've removed part of it too. And I think the same thing's happening here with the ICA-J. When you separate two people with that method, you're not looking at the same thing you would with independent radars. You've filtered out some of the good stuff too. So it's something that Mahmoud's kind of worked with, and at first we were worried that was going to be a showstopper, but he managed to redefine the the dynamic segmentation and such that was not a showstopper. Anyone else with more questions?
Well, I can ask just a, a curiosity question. What would happen if you don't have just 2 radars, but you have a whole array of radars? How far you can push the number of people that you could actually distinguish?
So it depends on the power of that particular radar system. Like here in the slide, I can see we use like the antenna power was like around 18 dBm, 13 dBi, and we found based on our measurement, like up to 3 to 4 meter, it works fine. But we also see in another project, I didn't do, but I saw, like I was also working in another project for occupancy sensing, where I saw that even at 7 meter and 8 meter, like quite close, less than, I think, less antenna gain, even can distinguish the breathing rate and heart rate. So,
but I think the question is, how many people can you separate?
So,
right. So you talked about the
not limited, but just 2 radars. You know, you're given the opportunity to implement a number.
Right. So 2 receiver elements, maximum I can do like when there is a 2 receiver elements, I can do maximum, I think 1, like maximum 3 probably, because I can, so if I use DOA, then 2, but if I use ICA jet, based on the result, I can do also 2, but I'm not sure how many people can be accommodated within beam, because we're still like investigating that. I'm not sure like how many participants can be accommodated, because you know the beam width here we are using like 30 degree, but another radar, the Professor Yao Zheng bought, is beam width like is 45 degree. So if beam width is like wide, probably we can accommodate more participants. And I'm not sure like how to quantify the number, but based on antenna resolution limit, spacing limit, probably for 2 receiver elements, we can distinguish 2 subjects maximum based on their direction of arrival.
Okay, how does the distance to the subject?
Mahmoud, we have people who've joined the talk, but at a point where we can't have people joining. Could you remove them?
I'm sorry. I'll get out. I didn't.
Sorry about that. We've passed the audience participation part.
It's all right. I'll leave. Sorry.
Sorry, Ashik.
Yeah. So good luck. Sorry. Thank you. Yeah. Good to see you all.
That was the second thing I had in mind when I set up the separate Zoom, but I figured, we don't need it.
I think.
Okay, sorry about that. I interrupted you.
Yeah, so it depends on the antenna power, but with our system, within beam, we did like, we can accommodate 2 participants.
Okay, and the second question regarding the COVID, I guess the most interesting is to recognize severe cases, like people coming with pneumonia.
Right.
This is the pattern you really care about. The rest are not interesting. The rest will just get better. They don't need hospital.
Yeah, I think actually we talked to a physician about this early on, and at some point when it gets bad enough, the way we recognize sleep apnea, a similar thing will happen to a person's breathing. Their diaphragm will break down, and it won't allow for, you'll get this paradoxical breathing. So the early screening point is the point where you don't know they have COVID, but you know they have something that's suspicious enough that maybe you ought to be swabbing their nose or something. We can't do the full diagnostic, and I guess if they're really sick, it doesn't matter what they're really sick from. You want to be worried about it, but it's a good point.
Okay, that will be all from me. Thank you. Nice presentation, by the way.
Thank you.
Olga, any questions for Mahmoud?
Yeah, so I have a quick question, Mahmoud, on how you handled millimeter wave data. So when you showed us the braiding signals, you showed us the amplitude in millimeters or centimeters. It looked like about a couple of centimeters, which is what we would expect. So I was just wondering, I'm assuming you used arctangent demodulation, and I was just wondering how did that process work because of the phase unwrapping, right? There's some ambiguity at higher frequencies.
Right. So what I did, like, the phase unwrapping, before separating the independent respiratory pattern, what I did, like, I did the unwrapping. I used the unwrapping function from the MATLAB. So each and every time, I also looked into their, like, after DC removal, I looked into their whether there is any kind of drift, and then I looked into their like phase imbalance and amplitude imbalance both, and then I also did the arctangent demodulation. So one thing I found, like, sometimes you see the subject B here. So I found, like, for some participants, sorry for that. So I found that, like, for some participants, so they showed, like, less displacement. And for some participants, like, their depth was much more higher for using 24 gigahertz, but maybe 2.4 gigahertz, I didn't see, like, that much of deviation. So that's another thing, like, helped to also, based on millimeter wave radar, probably its sensitivity is much higher. So that's why their, like, depth and other features is much more distinguishable than 2.4 gigahertz probably. But we didn't do any, like, any comparative analysis with these two radar module.
Right, so that was actually going to be my next question on what would you feel on 2.4 versus 24, because this is something that, we have looked at a couple of times, but I don't think we got any definite answers on is there a benefit, or we would probably have to do some sort of cost to benefit analysis to see what are the advantages of using 24 as opposed to how much computational complexity does it add, and
so
yeah.
Right. So that's a good question, I would say. So from my point of view, like, if we want to see what I understood, like, you see for 24, I can, based on my analysis, I can see, like, much more heart related feature, much more dominant. Even I used, like, 76 to 81 gigahertz for my internship at onsemi. I can see, like, in this particular peak point, I can see, like, much more ripple for higher frequencies. So my understanding is, like, probably I didn't do any kind of quantification, so I don't know. But for here, you see, for triangulation method, I took the maximum point and the 2 consecutive minimum point. So based on that, variations helped me to get, like, better accuracy also. I think in terms of heart related information extraction, probably higher frequency might be better, but I'm not sure, like, is there any other, like, health related issue or any other effect? I'm not sure about that. So I looked into mostly the respiratory variations, but I didn't know like how their other performances, like their distance sensitivity, will change. I didn't do any analysis yet. Yeah. So I just focus on the variation in their pattern of the different participants.
Right, but I mean, it sounds like from what you're saying that you didn't find that demodulation particularly challenging, right?
Not that.
Yeah.
Right,
okay.
not that much.
Could you show us one of your early slides where you show the IQ plot of the arc and how that?
Right. So I think this one, right?
Yeah. So with this one, you can see that arc is some small percent of 360 degrees. So that's displacement is not too big compared to the wavelength.
Right. For 24, the arc is, like, much bigger. It's like a total circle. But I think MATLAB has recently I think from 2019 or 18, they introduced new unwrap function. So unwrapping function like can take care of that. But before that, we have like separate function for that in our lab.
Yeah, and so it was always kind of problematic. And I'm wondering if that the way they've done it is helpful. The reason I say that is if you look at this one, you're showing the demodulation technique right there. There's a point you're calling the center of the circle, and you figure out the arc from that. We don't know that point, right? We have to estimate that point, and then we can figure out the arc once we've estimated that.
Right.
And that's not so easy to estimate, right? And it's drifting around. So
we use algorithm like center estimation algorithm.
Yeah. So I'm thinking the more wraps you have and such, I don't know if that's helping with center estimation or hurting center estimation. It's a good question, and you know, that's the reason why I'm wondering if maybe there's something to this that's actually improving the center estimation when you use a signal that wraps around many times.
Right.
I understand that you are trying a new method using Wi-Fi, right? Wi-Fi is sending an OFDM signal. That means you have a wideband signal get separated into multiple subcarrier.
Right.
And for each of the subcarrier, your phase offset is actually different. So your unwrapping might be easier with your Wi-Fi signal because the phase ambiguity gonna be there for one subcarrier, but it won't be there for another subcarrier.
Oh, right. That's using OFDM, right? So subcarrier will take care of that, right? Phase unwrapping problem will be less, right?
So better bandwidth give you a better unwrapping.
Okay. Any more?
No. Okay. Thank you. That's all I had.
So I think we covered most of the things. I wanted to ask you something about your opinion on this. This is a very nice application. The sleep one makes it kind of, it needs all the things that you're looking at doing, right? It needs the features you're creating, but it doesn't make the most challenging scenario for each of those. So that's nice. But you know, you compared at the beginning to a fingerprint for authentication, and for authentication, that's working out all right. But a fingerprint is more powerful than it can actually identify one person, you know, from many infinite number of people. I wonder where you think, you've looked at a lot more of these signals now than anybody. Where do you think it lies the limit in terms of identifying somebody from a breathing pattern? Do you know, right? We've talked about if you have 10 people, which one of the 10 is it now? That worked out pretty well. But how powerful, do you think that's powerful enough to really, you know, give you like a fingerprint ID or somewhere in that realm?
Right. That's a great question. So I think for fingerprint, one of the benefit is like it's not controlled by central neural mechanism or any kind of chemical feedback loop. Whereas breathing is like changing based on our mood or based on our physical activities. So the analysis so far we did is like just for sedentary respiration pattern, but I believe if we can integrate much more like features, like that's called fusion of different feature topology, if we can do that, probably we can make this system much more robust. And maybe for different physiological stress, maybe we may find like some more unique features. And at the same time, probably like integrating some other technique may help. But one problem is we don't know like how for different people, like how based on their emotional stress, like how it's going to change and what maybe the like other features we can look at. I still don't know, but based on the analysis, I think still there is a like good chance, and we need to do more testing probably for different scenarios also.
Yeah, it's a parameter that's in flux, and it probably changes too over time. It changes over the course of the day, how nervous you are, and as you get older, maybe things change too, especially if you're growing, right? So it's not the simple problem of you know, looking at somebody's eye or looking at somebody's fingerprint, which is kind of, it's there, it's fixed, but still, you found an awful lot of information here, and I think you did some tests also. What you looked at a person, and then you looked at them again after they'd gone up and down the stairs, and you still tried to see if you could identify them.
Yeah, so we did some experiments like for, I think, I have extra slide for that. Yep. So we did some experiments for, I think, 6 different participants, where we can see that their axillary like changes in a consistent manner. and breathing depth changes. And that's like for different participants was quite unique for 6 different participants. Even they are taking this test like once they are taking the in front of the radar system for just sedentary respiration pattern, then in the next week, they are walking to the upstairs and then they are taking that experiment. So then we mixed up the respiratory features for sedentary and for the after performing post-physiological activities features. And still we can see that here our accuracy was like for almost 92% for that particular case. So I think the machine learning classifier can also learn from the sedentary respiration pattern behaviors, and that can also help to identify from other after performing other post-physiological activities as well.
Your learning data, normally do you just need to see a few cycles of breathing for learning, or do you?
Right. So I changed the like capture duration, different window, sliding window. I found that at least like 13 to 14 seconds. Within that 14 second, we can get like, I think at least 3 breath cycle or 4 breath cycle can give us like quite good accuracy, above like 89%. And if
you did twice that, does it get better, or is it?
Right. Whenever we increase, because we are taking the average of different episodes area ratio, and like we are also calculating the inhale and exhale speed. So whenever we are increasing the breathing cycle, basically we see that the variations becomes much more dominant, and that also increases the classifier accuracy as well.
Yeah. So what would you think, like for the kind of work you've done, when do you think is a long enough stretch to have to start to max out in your accuracy?
Right. So if we consider about the like authentication time, that we need to do it like little bit faster, probably based on my analysis, 12.8 seconds or 13 seconds would be enough to get a reasonable accuracy, like approximately maybe above 90% within 13 seconds, and machine learning classification can take place like within 1 to 2 seconds. So 13 to 15 seconds would work. But if we want to make sure that accuracy should be much more higher, probably we need to increase that particular window size of the respiratory pattern. So 13 seconds gives us a like quite good accuracy, almost above 90%.
So that's a good result, but that's for how long you look at somebody for the examination. But I'm just saying, like in the original part, that when you were learning what they looked like, would your results have been better if you had more learning data? I'm sure there's some point of diminished return where you could say, if I see this many breathing cycles learning, more than that doesn't really help with the accuracy. And then the other end of the question is what you're showing right now is, once I have learned, how long does it take to recognize them? So, but learning, I'm just wondering, like often I see your learning are actually rather short, and I'm thinking because you've reached a point of diminished return. But when do you think, how much learning is enough learning before it doesn't help to do more?
Right. So for our case, like I used almost, I think 40 data set for training, and another 20 data set, or I think 25 data set for testing. So it depends on classifiers. So I also check the learning curve. So sometimes it may happen that if we put much more data set, probably it can do the like overfitting can occur. Like it can memorize all the features, but it cannot understand the relationship between features and the participants' breathing pattern. So based on
overfitting,
right, overfitting and underfitting may occur if we put like, so I think 40 different data set gives us like quite reasonable accuracy. But if we feed much more, like 50, probably overfitting may occur. At that point, like the classifier will learn, but it will not understand the relationship between the features and the subject's respiratory pattern.
All right. Well, I think I've asked everything I can think of. So if there are no more questions, maybe at this point, Mahmoud, if you could make sure I'm set up as the default coordinator, you can leave the meeting, and I'll text you or email you or something back to call you back in a little while.
So, do you know how to do that? I don't know, like how to make.
I think you can make another person the host.
Okay, so I'm stopping sharing.
So you can right click on the person. Is there like a make host option?
Yeah, yes, I got it. I think, yeah. Make host, yes. Okay.
Can you also stop the recording?
Yes,
please?
sure.